So this seminar is going to be presented by Fernando Medeiros. He is currently a doctoral researcher at the Center for Energy Resources Engineering in the Technical University of Denmark. He obtained his master's degree at the Chemical and Biochemical Engineering program at the Federal University of Rio de Janeiro, while working as a research engineer here in Atoms. His research interests include statistical thermodynamics, clatrate-hydrate modeling, and phase equilibrium calculations. He's currently investigating phase equilibrium calculations involve chemical reactions for reservoir simulation, and he's going to present some of his latest works now. Thank you, Fernando. Please go ahead.
Hello, everyone. So first, thanks for inviting me for this seminar. It's very nice to be here with you guys once again. So as you mentioned, I am a PhD student. So here I'm gonna share with you the things we have done so far in my PhD. So this first year of the PhD. So the talk is entitled State Function-Based Flash Specifications for Open Systems. And I'm gonna show some applications to CO2 underground storage. So first of all, what is CO2 underground? Sorry. Wait.
You don't have your share.
Oh, sorry. I was. Can you see it now?
Yes.
Okay, sorry. So
perfect.
Yeah, that was the first slide I showed, and this is the second one. I'm sorry. So basically, CO2 underground storage is one possibility in order to control CO2 atmospheric levels. So according to the Intergovernmental Panel on Climate Change, it is one of the most promising alternatives. And here there are several different possibilities for it. So basically, CO2 could be injected in depleted oil and gas reservoirs, as you can see here, or could be used in enhanced oil recovery, and also in deep saline aquifers. So deep saline aquifers are mineral formations that have water as a fluid there, and this water is rich in salt, so it's basically brine. And there is a lot of interest in this topic, and this can be seen by the number of papers that can be found in literature. So basically, since the 2000s, like the interest in it has been growing a lot. And my focus, like what I want to understand here, is how to simulate those processes. So many different phenomena take place in CO2 storage. So we can, for instance, think about how the geological medium is. So if the reservoir is heterogeneous, how permeable it is, the porosity, and so on. We also have thermodynamics from the point of view of the mixtures, CO2, like how CO2 interacts with all the components there. But we also have one of the major features, which is the reactive part of this process. So once CO2 is injected in mineral formations, several reactions can take place, especially if water is present. So CO2 can dissolve into water, which is a physical process, but then once in the aqueous phase, it can react and form carbonate or other ionic species. So basically, there are several things playing a role here. And this next slide is about how the different models, how every part of the process is being modeled. So basically, there is an outer part of those simulators that is related to flow equations. So basically, in nature, they are partial differential equations with space and time. So here you have like all the connections between different cells, how the flow goes from one cell to the other. Then there is this inner part here, where slow reactions occur. So basically, reactions in those processes, they are separated into fast reactions and slow reactions. So slow reactions are usually dissolution reactions. So minerals, they interact with water and they are dissolved into water. So this dissolution is a reactive process, and it is considered as a time-dependent process because they're slow. But there are other reactions that are fast enough, so they are considered always equilibrated, like the speciation reactions. So reactions that happen in the water phase typically. So as I mentioned before, speciation reactions and so on, they are considered fast, and the dissolution of the solids is considered slow. So precipitations and changes in solids. And basically, what I'm going to talk about in this presentation is about this inner part here, equilibrium calculations. So I'm only going to talk about fast reactions and how they change the system, how to model them. Basically, it's done here by a minimization of Gibbs energy, but how is it done? And typically, it's an algebraic system, yeah, that we solve. So first of all, a quick recap on how phase equilibrium calculation works when we don't have reactions. So basically, mathematical formulation phase equilibrium problem at TPN, when we have fixed temperature, pressure, and number of moles, is through the minimization of Gibbs energy. So Gibbs energy is the system, and there is this constraint of number of moles. So number of moles in every phase should be equal to the total mole numbers that is loaded into the system. This is pretty much how it works. But in reactive systems, there is something else, because there is no conservation of mole numbers. So for instance, I have this reaction here, A plus B equals AB. So the number of moles of species A is not constant if this reaction moves forward. So we have this consumption of A and also a consumption of B that leads to a production of AB. So something else, like mole numbers are not being conserved there. So what is conserved then? And if we look closely, we see that the building blocks of the species are being conserved. And what do I mean by building blocks? So we have A, the species A, reacts with the species B, and then they form the species AB, but there is no consumption of A or B. We still have the same amounts of A and B. And that's pretty much what characterizes those reactive problems. There is a conservation, but not a mole number conservation, an element conservation. And that's why in this equation here, I have framed the problem a little bit differently. So we have a Gibbs energy part here by the sum of chemical potentials. We also have this restriction here. It's a Lagrangian problem. I have formulated it as a Lagrangian problem. And this lambda here is the Lagrange multiplier related to all the restrictions and elements. So basically, there is a Gibbs energy minimization, but this minimization is constrained by this element balance. And the conditions you see here, those two derivatives here that have to be equal to 0, they're called the Karush-Kuhn-Tucker conditions. So in optimization theory, constraint optimization theory, they are well known, and they have this name, shortly called KKT conditions. And in order to get to the solution of the system under those restrictions, we have to solve for those KKT conditions. But how do simulators handle this problem right now? So there are several simulators that are capable of doing it, and I have named some of them here: Freaksy, EQ3, 6, and the Geochemist Workbench. So all of them, they work with a similar formulation of the problem. So instead of framing it as a minimization problem, they have residual functions that they solve. Of course, those residual functions, they come from a Gibbs energy minimization background, but they're not exactly the same. So it turns out that the problem is not really solved as a minimization problem, but as a root finding problem. So here you see what they call law of mass actions. So for people that have studied thermodynamics, classical thermodynamics, this K here is what we call equilibrium reaction constant. And we know that it's related somehow to the chemical potentials. And there is this product here of molalities and activity coefficients that are molality based. And this is the stoichiometric coefficient of this component I in the reaction. So basically, this is the typical equation that they work, the law of mass actions. And on top of that, they also have another conservation equation, because those algorithms, they work with distinction of species. They have secondary species and primary species. So the primary species are basically elements, and I have used the same variable here, the B variable. So basically that's how they work. But there are also, too much. There are also other simulators that are based on Gibbs energy minimization. Like they actually use the variables that for which the minimization was cast. So some algorithms, they solve directly for KKT conditions like Leo and Kulik. Some algorithms, they use null space methods. So null space methods, they are a typical methodology used in constraint optimization. And they make use of this relation here. So you saw before, I forgot to mention, there is this A here. This A is the formula matrix. It basically says how much of an element is present in a species. So that's why this is the matrix that makes us able to relate, like to make the relation between the species and the elements. And because of this relation here, the formula matrix and the stoichiometric coefficient matrix, we are able to frame the problem using this variable here, the extent of reaction. So this is another branch of those algorithms, but there are also range space methods, and those are the ones I'm working with, that I'm working on right now. And among them, there are the RAND methods, and I'm going to talk a little bit more about the RAND methods. So basically, the KKT conditions are formulated into a two-step algorithm. So there is a system solving step for where the system is solved for the Lagrange coefficients, Lagrange multipliers, and also for the amount of phase. So this is a multi-phase problem, and there are several updates for the phase amounts. And this M matrix is related to the chemical potentials. So basically, once this system is solved for lambda and delta beta, those variables are used to get values of delta N. And then the mole numbers are updated, M is updated, and this system is solved several times until convergence is achieved. So at the beginning of my presentation, I talked about open system calculations. So what do I exactly mean when I talk about open system calculations? So basically in thermodynamics, we typically work with closed systems. So, and we try to think of systems as the boundaries that it has. So if an isolated system is a system that doesn't exchange energy or mass or volume, but here, when I'm talking about open system calculations, I'm talking about this system here that you see this in this box here. This box has a control of pressure through this piston, and also a temperature bath. So basically, temperature and pressure are being controlled by energy and the volume of the system, by those changes. But there's also a semi-permeable membrane. And this purple molecule here can go in and out of this membrane. So that's why the system is called open, because it can exchange matter with outside. And why is it important in CO2 sequestration? So this is a plot that is common in that kind of literature in order to understand what happens with the mineral formations once you inject CO2. So basically, in this plot here on the left, you can see phases that are changing due to a reaction. So there is a reaction process here, and the amount of phases is changing. So basically, the system is open to a CO2 reservoir. And chrysotile, this solid here, is being titrated into the system. So actually, we add a small amount of chrysolite and see how the system responds. So this is very interesting, a very interesting way to assess like how many CO2 can be trapped into a mineral formation, like what kind of mineral formations are interesting for, like are better for trapping CO2. And now this is the big question that I'm gonna try to answer in this presentation. So root finding algorithms solve this problem by adding extra equations. So they basically just add chemical potential restriction. But since I'm working with Gibbs energy minimization processes, is it possible to solve this system through this perspective as a state function minimization problem? So now I'm going to open like a very big parenthesis, and I'm going to stop talking a little bit about geochemistry, but at the end of the presentation, I'm going to go back to it. So basically what happens, this problem in geochemistry is a very typical problem, because the models that they use are based on temperature, pressure, and number of moles. So basically, they use Bitzer's method, Brownlee's method. So basically, excess Gibbs energy models that are TPN based. But when we have open systems, we are not working with Gibbs energy anymore. So the variables that have to be minimized, like the variables for which the minimization problem is cast, is not really the ones of the model. So this creates a problem that was solved by Michelson in 1999 for closed systems using this Q function approach. So that's what I'm calling here Michelson's Q function. So if we think about a UV flash that is being modeled by a TPN based model, so for instance an equation of state written in this way, we have something like this. So we have TPN, and then the model gives us all the variables that we are interested, that we can take from its relations. And here I have just selected a few that are important for this application. So basically entropy, volume, internal energy, chemical potential. But what happens is in a UV flash is that I have an isolated system fixed UVN. So here I have phases, so because they're not the same as the variables of the model. So how to build those Q functions? Following the same example of the UV flash, I have here the TPN-based thermodynamic models. We know that we have to minimize minus entropy. It's the maximization of entropy in this case, with a closed system. But the variables I'm going to minimize for are temperature, pressure, the internal degrees of the model, of the system, like the number of moles in every phase. And just a second, is there any problem with the internet connection, or?
It cut a little bit, but it's nice, I think.
Okay. But I mean, have you lost any kind of do you want me to go back, or is it okay?
No, I think you can continue.
No, it's okay.
Okay. So basically that's the problem we're dealing with. So minimization of S, of entropy, with respect to temperature, pressure, and the internal degrees of freedom of the system. So the number of moles in each phase. But there are some restrictions now, because we have to meet the specified U and V that actually makes this maximization of entropy problem. And also this final one here, this final restriction, is basically just the sum of the molar amounts in every phase should be the same as the total amount of phases that we have. So that's the problem we have when we use different types of variables in the model and in the minimization problem. And how do we solve it? Here, again, there is a Lagrangian function. So basically, there are two restrictions, as we saw before, extra restrictions. So one for internal energy and another for volume. And here we have the Lagrange multipliers related to those restrictions. And we know from constraint minimization theory that the Lagrange multipliers at the solution, they have a very specific meaning. They mean like the marginal change of the constraint. So how the function changes with a change in the constraint variable. So that's what they mean basically from constraint minimization theory. And we know from thermodynamics that this is a very well-known variable, -1/t, and the same thing for volume, -p/t. So this comes from the fundamental relation of thermodynamics, written in this way for entropy. So basically, we replace them. We replace the Lagrange multipliers by those variables that we have here, and that's what we get. We get the Q functions. So this is no longer a strict Lagrange problem because we have used one of the restrictions at the solution before achieving the solution. So it's a little bit tricky. It's not actually a Lagrange multiplier problem, but it's similar. And here we can perform this manipulation here. So by just multiplying 1 over t with u and so on, we can get Gibbs energy, which is actually the energy for which the model was derived. So the model is TPN based. So it's a Gibbs energy based model. And then we have Gibbs energy and this relationship here in order to have Q, the Q function to minimize. And those are the sets, the set of Q functions that Michelson proposed in 1999. So basically they are, in order to form them, you have to perform Legendre transforms. So from the state function you have, the state function your model gives, so basically Gibbs, and the state function you're trying to minimize. So by performing the equivalent, the corresponding Legendre transform, you arrive to the Q function that you have to minimize. And some of those Q functions, they generate minimization problems or saddle point problems. So it's a little bit tricky to know when they are minimizations and when they are not. But basically, sometimes we're lucky enough to get minimizations and to use all the tools in minimization algorithms that we can use to get to the convergence. So how about open systems, right? Because that's the focus of the presentation. So the thermodynamic potential that we have to minimize in open systems is this GQ. So what is GQ? It's basically G with the corresponding Legendre transforms for the fixing of a chemical potential. So here it goes from 1 to the number of fixed chemical potentials that I might have. And that's the potential that we have to minimize. And people, like, we know that if we fix all the chemical potentials, then this becomes 0, and there is nothing to minimize. We get to the Gibbs-Duhem equation of states. So we have to be careful to always have at least one extensive variable in our potential, because if we change all the n's to chemical potentials, and we have temperature, pressure, and chemical potentials, then we have only specified intensive variables, and we don't know the size of the system because there is no extensive variable being fixed. So yeah, that's the potential that we have to minimize, and it can be shown. I'm gonna spare you from all the tedious mathematical derivations because there's already enough, I guess. The Q function for open systems, this one on the left-hand side, is basically the Q function for the closed systems minus the specified mu times n. And this is an extensive list of all chemical potential, all the variables for, actually all the Q functions for open systems based on Michelson's original Q functions. So basically, with this set of Q functions, all the transformations are possible, because if you think about the fundamental relation of thermodynamics, Michelson only worked with temperature and entropy, pressure and volume. So he only switched one with the other, the conjugate variable of pressure, the conjugate variable of entropy. And now what we have done here is working with the other missing part of the fundamental relation of thermodynamics, which are the conjugate variables, chemical potential, and number of moles. So now, like, the usual variables are all covered with this set of Q functions. And one thing that we have to notice is that all those sets of variables that we have here, they are sets of variables that have corresponding thermodynamic potential. So for instance, there is no PV problem, because PV, although we know that we can solve and find a root for a specified pressure and volume, this doesn't correspond to an energy or a potential to be minimized. So there is no, this selection is not here. Yeah, so those are the open system Q functions. But now I'm gonna open another parenthesis, even though I'm talking about geochemistry. Let me just drink some water before I move on. So in order to test this approach, we have used a hydrocarbon mixture because that's what we're used to. And that's why I call it here proof of concept. So in order to prove this concept, we decided to use a two-phase flash approach for a hydrocarbon mixture. And what the Q functions, they exist, like it's just a matter of writing the thermodynamic potentials and so on, but how you solve it is up to you. So what we did is that we followed Michielson's two-phase flash approach in his original paper. So basically in Michielson's papers, he has this M matrix here related to chemical potentials, and his problem ends up here in this EPP element here. So this is the submatrix he has presented in his work. Basically what we did here is add this final row, column and row here. And what those things mean. So delta V is actually the vapor, the number of moles of the components in the vapor phase. Delta LNT is the temperature of the system, so the update in the temperature of the system. This is the update in the pressure of the system. And there is a delta Z, which is the update in the total mole number of the system. So how much of a component is entering the system. So basically, this is a change in the mole numbers of the phases so that we have the chemical potential equalities met. This is a change in temperature so that we have the energetic constraints met. So if we are working in the UV-based flash, this is in order to change to get to U. So this is related to the energy. This is related to the volume constraint, and this is related to the chemical potential constraint. And here I have there are the gradients that we have to solve, the gradients of the Q function, and those R's are here. So we use this, we solve this system here until we get to a stationary point of the Q function. And those are the RTs here that I have just for curiosity. So basically the RTs are related to energies and entropy. The RPs are related to pressure and volume, and the RNs are related to chemical potentials. So basically what I'm gonna show you next is a sub problem. It's not the complete matrix, but just the M part and this final part here related to the chemical potential. I don't have anything related to temperature and pressure. So just keep that in mind, it's a sub problem. In order to prove the concept, what we did was we basically performed just a regular two-phase flash for a closed system. So here on the right side, there is the abstraction of what type of system it is. So basically temperature and pressure. There is no exchange of matter of any kind. And it's a phase envelope of a 5-component mixture with methane, ethane, propane, and octane, and no name. That's what we get. So we get the betas here, the volume fractions. Here we also have the number of iterations. So it takes only up to 20 in order to get to the solution. And here is the fugacity of methane. So basically, we kept track of how the fugacity of methane was throughout the whole envelope. And why did we do that? We did that because that's what we're gonna fix in the next step. So we performed the phase equilibrium calculation for betas. Here you can see the iterations that it took. And here there are the fugacities of methane in each temperature and pressure. And now we kind of inverted the problem. So here's the abstraction on the right corner. Now methane can go in and out of the system, but temperature and pressure are fixed. So that's why I said it was a sub-problem of the problem I mentioned before, because I'm not changing in pressure, I'm not fixing other variables. So I'm having pressure and temperature constant, which are variables of the model. And I'm also now fixing methane's fugacity. So methane can go in and out of the system, and it's fixed. at the values presented before, as I showed you. And here, there's the same phase equilibrium, basically, the same distribution of betas, but a different iteration path, because it's a different problem. But at the end, all of those flash problems at every temperature and pressure should go back to 0.4 methane mole numbers, and that's what happened, basically. So here I have some convergence plots for this temperature and pressure. And as you can see, I also tried a first order approach with, like I turned off the derivatives of the chemical potentials with respect to mole numbers. And then I get this first order convergence here. And the algorithm I used has second order convergence, as you can see. And furthermore, it's a Q function minimization. So I'm actually minimizing it throughout every step. I'm minimizing. So all the tracks of objective functions can actually be employed here in order to ensure a safe convergence. And this is another interesting thing we decided to do. Basically, it's an open system again, but instead of fixing the fugacities, instead of varying the fugacities, I use just one fugacity of methane, so 0.6. So basically, there's this mixture here that is trapped into the system, 0.1 mole of ethane, 0.1 of propane, 0.2 of octane, and 0.2 of nonane, basically the same ones as before. So they are trapped here in this rectangle, and the fugacity of methane of the reservoir is fixed. So methane can go in and out, and the total amount of methane is going to change. And that's what we get. We get this very different phase envelope. So it has this tail here that goes all the way, that stretches all the way to the saturation pressure of pure methane. So basically here, the vapor, the betas, they change abruptly. So as you can see, all the lines, they kind of merge there. So the changes here are very abrupt. And this saturation pressure here of the pure methane is the saturation pressure at the fixed fugacity. So basically fixing this fugacity of methane in the pure component, that's the saturation pressure that we get. So it makes sense from a thermodynamic point of view. And this is the number of iterations. Actually, we went to 100 iterations close into this tail here because it's very hard to converge there. And here is the total amount of Z, so as the total amount of methane in the system. So as I mentioned before, the amount of methane is going to change because it's fixed at one fugacity. So in order to have 0.4 as I had before, I had to change the fugacities. But now since I have fixed it, I'm going to have very different values of the total amount of methane. So basically, this region here is mostly pure methane, and here it's very, very poor in methane, so almost pure methane, but not really, because if it were pure methane in this region, it wouldn't have two phases, I guess. So yeah, it makes sense thermodynamically speaking, but it's a very different plot. And then we did this for open systems, reactive open systems. So that's the huge Q function that you can see there. So basically it has Gibbs energy part, it has the conservation of elements part, and here I included temperature and pressure just to have the complete set of possible changes that we can make. And that's how the RAND algorithm looks like for open systems. So before it was just like those 4 elements here. This is if there is any energetic change related with the pair temperature, entropy, or temperature energy. This is related to the change in pressure and volume. And this is for the open system. So for the open system, it's quite simple. It's a quite simple change. Just need to use the same formula matrix as before. But for the specified component, the component whose chemical potential is specified. And then what appears here is the amount of that component that entered the system. And the update in mole numbers is still the same. Again, we performed this, the same kind of test. So up here, in the corner, I have the abstraction. So for a closed system, we had this reactive mixture of water, propene, 1-propanol, and propane. So basically water and propene, they can react to form 1-propanol, and propane is an inert in this system. And there is a two-phase region here. So a two-phase region between 270 and 345. So that's the profile that we have for the phase fraction for liquid and vapor. This is the molar fraction in the liquid phase. This is the molar fraction in the vapor phase. And this is the dimensionless chemical potential. So in order to test it, we just inverted the problem as before, and we fixed the fugacity of water. So the fugacity of water, the chemical potential of water, was fixed at those values here. Water is component 4. So those values here were fixed. And we obtained the same plots as before. They are exactly the same plots as before. So it shows that we're solving the same problem through a different perspective. And it also has quadratic convergence. We see from different temperatures here, temperature 260 to 300 Kelvin, 350 Kelvin. So everything is quadratic, and yeah, it works, and it's quick. And as I told you, I was opening a parenthesis in the beginning of the presentation. I was talking about geochemistry, and then I opened this parenthesis, and I talked about mathematical derivations and a lot of things there. Then I talked about hydrocarbons, and now finally I'm closing this parenthesis, and now I have the plots related to geochemistry. So they're still preliminary somehow, so I don't have that many details here. But basically what's going on is that I have a system that can form dolomite, quartz, or calcite, which are different solid phases. And what I'm doing here is, and also water is present, so there is a water phase. There are no other phases, just the solids and water. And what I'm doing here is that I'm changing the pressure, but not really the pressure. I'm changing the chemical potential of CO2 by changing the pressure. So what this is actually the pressure at which my chemical potential, my CO2 chemical potential, is being calculated. So basically this means that, for instance, at 5, I have a reservoir, a system filled with water, but in contact with a reservoir of CO2 at 5 atmospheres. So basically my system here, if you can see the pointer, my system here has water, and this reservoir of CO2 is now at 5 atmospheres, and CO2 can go in and out of the system. And that's what's going on. So here there is a dolomite and quartz region. So dolomite, quartz, and water are present here. Then after around like 14 atmospheres, calcite precipitates, and there is the appearance of calcite. And the dots here are Frixie. As I mentioned, Frixie is one of the benchmark simulators in this area. And we managed to emulate, to have the same results as Frixie using a different methodology that is based on this Q function minimization and Rand algorithm. And here I also have the molality of the aqueous phase. So this is how the aqueous phase composition changes with this change in chemical potential of water, not water, but CO2. So basically you can see that as the chemical potential goes up, I have more CO2 entering the system. So this is the amount of CO2 that enters the system. And here you can also see that the molality of CO2 is also increasing, the molality of dissolved CO2. And here there are other carbonated species. So some of them actually decrease this ion related to CO2 because of the reactions that are going on. And here are the phases, so how the phases change. So basically, dolomite's being consumed a lot as I increase my CO2 pressure. So basically, I'm dissolving more dolomite as pressure goes up. And quartz and calcite actually is precipitating here, so there is a slight increase here in calcite, and quartz is almost constant throughout the whole range of pressures we have studied here. So that's the geochemistry example that I promised you in the beginning, and finally it's here. So now the conclusions of what we have done so far is that we have extended Michelson's Q function approach to open systems. So now we're capable of working with all major thermodynamic variables in the fundamental relation of thermodynamics. So entropy, temperature, they can be switched. Volume and pressure, they can be switched. And now chemical potential and number of moles can be switched in this framework. But also, I mean, there are other additions that can be made. So for instance, we can include, for instance, surface area and the interfacial tension. It can also be there in those calculations. So basically, if the model is based on, I mean, you can change all the specification based on the model you're using for your interfacial change tension. I mean, it's quite speculative, but just thermodynamics is not only about temperature, pressure, and only the usual variables that we are thinking about. And also we managed to pose the problem, the open system geochemical problem, as a minimization problem in the scope of the range space methods, as I mentioned before. We could have used other methods, but since we are working with range space methods, that's what we did. We increased we extended the RAND method to those open systems. And now I'm wrapping up the presentation, and I would like to start the discussion already. So are there possible applications for this? So mainly, I think mainly about chemical potential, fixed chemical potential applications, such as compositional grading, for instance, that has a gradient of fixed fugacities based because of the gravity, the gravity segregation of fluids. Also membranes. So sometimes we have processes involving membranes. So it's just applicable to those processes. And finally, also confined fluids. Sometimes we have TVN-based thermodynamics, and we're actually specifying chemical potentials. So those are some of the things that, yeah, we can discuss perhaps. And thank you very much for the attention and for being here with me through this presentation. So thank you a lot.
Thank you, Fernando. Thank you for your presentation. It was really well presented and nice pictures. Those colors were captivating. So I'm going to open for discussions now. Some people are going to post in the chat, and I can read.
Can I ask?
Yeah, Fred, you can be the first one.
Yeah. And thank you. I think it's very, very interesting, and I think you did a lot in 1 year.
Thank you.
Yeah. I think it's open for a lot of applications, this kind of strategy, and especially in atoms. I think there's a lot of people that may be going to talk with you about this, details about this strategy. I wonder how much did you use for your development in 1 year, that fast? How much did you use your statistical thermodynamics? Because it looks to me very similar to grand canonical ensemble or semi-grand canonical ensemble. So I want to comment about this.
Actually, those ideas, they actually came from what we have been working with in the masters, like the gas hydrate problem, which is a problem with other specifications. So those were things that were in my mind somehow. And then when I started studying those RAND problems and the RAND algorithm and the geochemistry part, I realized that it's something important for those people. So perhaps the Gibbs energy algorithms in that area, they're not that common because there is no such application that is very important for them. So there are some algorithms that Gibbs energy algorithms that are capable of doing this, but perhaps not in the best way possible. So I was, because of this idea and this experience with gas hydrates, which is a problem where you specify different variables. So the model is not TPN based, but it's fugacity based because of the fugacity of the gas phase. Then all those ideas, they were in my mind somehow. And then seeing this problem, we were able to do it. And yeah, basically it was studying this equilibrium part, and we managed to do that. But the development was like this first year. So we did this in yeah, because of the coronavirus crisis also, I had some time to get more results and so on. So yeah. Not sure if I answered the question.
No, yeah. Sometimes coronavirus help us.
Yeah. There's nothing much to do, right? So yeah.
Fernando,
Hi.
can you hear me?
Yes, I can.
I'd like to thank you for your presentation. It was very interesting. I would like you to comment about maintaining a neutrality in the system. Is it naturally achieved, minimization of Gibbs energy, or is it imposed somewhere else in the model or something?
It is naturally achieved because of the formula matrix. So the formula matrix is the matrix that tells us what kind of species what species have what elements. So and also the reactions. So your reactions, when you have them in the system, in my algorithm, for instance, what do? I have a set of reaction stoichiometric coefficients. So all my reactions, they are listed in a matrix of stoichiometric coefficients. And then if they are balanced there, so if all the equations are balanced already there, then when the formula matrix is created, it is created somehow, it is created in a way that the electron neutrality is always respected. So it's kind of a hidden constraint in this approach. So there is no, I don't have an extra equation for electron neutrality, no.
Thank you.
And also the species I'm adding in the system, in those systems that I showed, they are uncharged. So CO2 is being added, but there's no charge in CO2, so it doesn't violate electron neutrality also.
Yeah, if you added salt, then you would to obviously add both cation and anion at the same time to maintain the electron neutrality of the system. This would naturally occur, or
no, it wouldn't. Like the addition wouldn't be, because for instance, imagine that I'm specifying the chemical potential of a charged species. So I'm specifying this chemical potential, and then I have to add this amount of this charged species. So there are several other species that can be added together with that in order to maintain electron neutrality. So basically, if it's charged, I have to have a counter ion entering the system. Yeah.
So you would vary some of this, any of the salts present, and you would add sodium chloride or sulfate or something like that.
Exactly. I think there are molecular simulations on this, like that they keep pH constant. So they keep the pH of the system constant, but then they have to include a counter ion. So I think all those problems are always tackled in that way. Yeah.
Thank you.
Have you published or read something about this?
I have submitted.
Are you writing?
I have submitted one paper to the AICHE journal, and there's also another publication we're still working on. One is more related to methodology and to all this part of Q function and hydrocarbons, and the other one is more related to geochemistry, like geochemical examples and what kind of problems we can find in geochemical.
Fernando,
Hi.
here, Papa, I have some concern about the computational times for open system. How do you use it?
Sorry,
I couldn't hear either.
I heard the concerns about computational time. That's
how much time you watched for maybe 3 phases or in 5 component system?
so I have performed this computational time analysis for geochemical systems, but it's still preliminary. It's not something like very concrete. It's preliminary. So basically what I did was I have those calculations that you saw, the calculations with dolomite. I'm going to share the screen again so that you can see. Can you see the screen, the screen here?
Yes, yes.
Yes. So this is a problem with dolomite, quartz, and calcite. So basically in this region where I have 3 phases plus water, so I have 3 solid phases plus water. So basically I start with a phase assemblage, sorry. And then from this phase assemblage, I perform an equilibrium calculation. Then I check whether or not there are saturated or undersaturated species. And then I add those, not species, but phases. And then I add those phases and I perform new calculations. So basically when this happens, like when I have to include a lot of phases, this takes some time. So that's what the most costly of the process is, to perform different equilibriums in order to achieve the final phase assemblage. And this is also important because in those systems, they most of the time they become unsaturated, like supersaturated, one phase at a time. So I have a phase assemblage, then I have to add another phase, perform a new equilibrium, then add another phase, and then perform a new equilibrium, and so on. So it takes a lot of time to discover this final phase assemblage. So this is the most costly part, but in all the scenarios I have tested, my algorithms are faster than Freaksy. So my algorithms, they are around microseconds, and Freaksy is around like 0.1 or 0.01 seconds. So we're performing faster than Freaksy, but I mean, it could also be implementation wise. I mean, those comparisons, they are sometimes, yeah, not about the algorithm itself, but about like the implementation, or how big Freaksy is as a software. So how many steps do they have that I don't have, because my problem here is very focused. So I don't, yeah, that's basically it. So even though it can become quite complicated when we have a lot of phases, it's still being faster than Freaksy, which is one of the benchmarks. Yeah, I hope I answered your question.
Thank you, thank you.
Any other questions?
I think someone wrote something in the chat, right?
Hello, Fernando. Can you hear me?
Hi, yes.
Oh, this is Danilo from IEEES. Thank you very much for the presentation. My question is also about the convergence. In the middle of the presentation, you shown comparison between first order and second order methods, and obviously that you reached faster convergence with the second order methods. But comparing just the number of iterations, it's one thing, but what about the cost of evaluating the hashing? When you take that into account, this comparison, what do you think about that?
Well, in that case that I showed, I didn't perform any kind of computational time. Like I didn't check the performance of the code. So I just showed you the iterations as you saw. But in that case, I don't think it's costly, because the the hashings that I have, they are all analytical. So the expressions I have, they are basically analytical expressions. So I don't think they are that they cost that much. So there is no matrix inversion. There is no numerical Jacobian being calculated or anything like that. So it's basically analytical. So from this point of view, I think the cost is minimal in that specific case. But in the geochemistry part, I'm using numerical derivatives for the Gibbs energy model. So in that case, they are costly. They are more costly, but still, even as costly as they are performing faster than the benchmark software. Yeah.
Oh, thank you. Thank you.
There is also a question here in the chat that I got about, I'm going to read it. I imagine that an open system might occur when the component coming from a reservoir is at a different temperature or pressure than the system. So even though the equality of chemical potentials can be enacted, the thermal equilibration might not. Does the framework account for those cases? So it's a question from Fernando Escobedo. So yes, it does account for it, because what I'm doing right now is just basically the chemical potential part is, even though it's a chemical potential specification, it's those chemical potentials are being calculated from a pair of temperature and pressure. So in all my simulations, I imagine like, okay, CO2 is at this pressure and at this temperature, and from that I calculate the chemical potential. So yes, I mean, there is no restriction in temperature. So the reservoir might be at any temperature and pressure, and the internal part might be at any other temperature and pressure different from that of the reservoir. Yeah.
So any further questions? Let me ask one. I don't recall if you mentioned any liquid-liquid equilibrium. So you work with CO2. So at high CO2 content, high pressure, you might have liquid-liquid equilibrium. And how is the algorithm dealing with that?
So that's a very good question, actually, because what happens is that those chemical potential, those fugacity specifications, they are very tricky. So in order to specify, I'm working with liquid phases that have ions. So the ions, they cannot go into a vapor phase. So even though my algorithm is capable of dealing with a vapor phase, the ions cannot go to the vapor phase. So I can only have a vapor phase once it's stable with only CO2 and water. Yeah, basically that's what happens. So in the closed system, it's easy. I just load all of them there. So if there is some CO2 that wants to move to the vapor phase together with water, a vapor phase appears and nothing happens. But when I fix the pH, not the pH, but the fugacity of CO2, then I might go into a region of fugacity that wants all water to go into the vapor phase. And when I get to this point where all water wants to go to the vapor phase and my system wants to migrate to a vapor phase, then my algorithm crashes, because the anions and cations cannot be alone in the water phase. So they cannot go into the vapor phase. So there's a very narrow window of chemical potential specification in which I achieve two phases, like two fluid phases, a CO2 and water phase, rich with CO2 in the vapor state, and also a water-rich phase, an aqueous phase modeled by excess Gibbs energy model. So that's a very, very tricky, very fine problem. I mean, in the hydrocarbon problem, I didn't have any kind of trouble with that, because I mean, it's an equation of state, so all components can be in all phases, and it's simple. If the phase doesn't exist anymore, then it's okay. But with the specification of fugacity of CO2, sometimes the water phase wants to disappear, but it cannot disappear because of the ions and so on. Yeah.
But in this case, you have a solid phase, so they can precipitate in a solid phase.
Yeah. Sometimes I have the solid phase and they can precipitate. That's true. But sometimes it just crashes. So it's something like I still have to work on that a little bit. I just said like all the water is gonna go up to CO2, and then to the vapor phase, and then all the minerals are gonna start to precipitate. Yeah, but it's still something I haven't solved. Yeah.
Yeah, thank you. Well, I don't have any further questions here. I don't know, maybe it's time to wrap it up.
Let just ask about the models. I use a pizza model, or I use something else?
I'm using Pitzer's model because the benchmark simulators, they have a lot of other models like WATEC and also Bromley's model, but I think some of them are not thermodynamically consistent. So if they're not thermodynamically consistent, they cannot be used in this Gibbs energy minimization framework. So there are some problems there, some consistency problems there. And yeah, but so far I have only used Pitzer for the aqueous phase and either SRK or Peng Robinson for the vapor phase.
Okay.
Fernando, I've read that's quite a problem because many more advanced models are thermodynamically inconsistent.
Yeah.
Like, for example, Enlighten RTL or an extended Uniquac, Unifac, don't know, for light systems. And they can't be used in Gibbs energy minimization approaches for equilibrium calculations.
I mean, that's one advantage of the root finding process algorithms, because they're just equations that you need to solve. So the equality is going to be attained no matter what. But yeah, this is a problem in this more rigorous framework, because everything has to be rigorous in order to use it to be possible to solve those chemical or physical equilibrium problems. Yeah, you're right. You're right.
Thank you very much, Fernando. It was a very enlightful seminar. Thank you very much.
And thank you all for inviting me and for the attention. Yeah.
Thank you. Bye-bye.
Bye-bye. See you.